And coming up right now is the Space Show.
This is your community radio station, 88.3 Southern FM.
Welcome to the Space Show, presented by members of the Space Association of Australia. Hello, I'm Andrew Rennie. The Swift Reboost mission has been launched, and we hear about the Western Australian Optical Ground Station. And we turn back time to 1966, and we have more about the Carmen project, depending on the Swift Reboost mission launch. Now, Space Show News. Last week, we were awaiting the launch of a satellite, which is going to boost another satellite into a higher orbit. Well, the launch got delayed, but eventually, on I think it was Friday, it got launched. Now, the idea is that this target satellite is called SWIFT. It's an astrophysics satellite, and at the moment, it's orbiting at around about 300 kilometers above the Earth. And if it's not boosted, it will drop below 300 kilometres sometime in October, and then will be beyond saving, as atmospheric drag will make it spiral into the atmosphere. It's falling at about 8 kilometres per month. Well, what's been launched on a Pegasus XL, dropped from an Stargazer L-1011 aircraft from the Marshall Islands, KwaZulu Natal in fact, a spacecraft called Link, which is designed to rendezvous with Swift, attach itself, and then boost Swift to a higher orbit, to around about 550 kilometres. So it's in orbit now, and will at some time in the future approach the Swift craft. Now, if this reboost is successful, Swift could resume science observations in the southern spring. Well, how is the Swift going to be captured? Well, at a press conference held on June the 17th, that was one of the questions that was asked.
We have Bill Harwood with CBS News.
Yeah, hi. Thank you very much. I think this is probably for Karen. Could you just walk us through, and I realize some of this is on the webpage, but could you just walk through the capture process? I mean, the appendages and things that have to work. I recall STS-49. If you remember, it was on Sat-6, and the astronauts tried to put a capture bar on it, and the thing tipped off and began wobbling, and it was very dynamic in terms of your references to, dynamic space ops. It strikes me this is pretty dynamic. So could you just walk us through the process of stably capturing the satellite? Thanks.
Yes, this is Karen Wilson. So one thing that we're relying on for Swift is its ability to maintain its own pointing and attitude control. So Swift is a unprepared but cooperative partner in the rendezvous. There's no features on Swift that are designed for capture. There's a lack of documentation to even help us figure out where those features would be if they existed. But we are confident that Swift can point well. That's its primary role as a telescope. And we've been working very closely with the Swift mission operations team to define attitude profiles for Swift to follow as we approach and inspect it. So once we get to within tens of meters, Swift will be performing maneuvers in tandem with us in order for us to inspect the capture locations, ensure that they are free of FOD, debris, torn off MLI, whatever may be there, and to essentially move through various capture locations that we have. We have primary backup, secondary backup options for features that we believe are suitable for capture using our robotics. We have a very versatile set of robotics. There's a unique robotic platform that we've developed over the last couple of years called the Split Stewart platform, and it's intended to allow us to capture a wide range of spacecraft with various configurations. So it has 3 arms, 3 independent grippers, which allow us to grasp 3 points on Swift. We can perform the mission if we only grasp with one, but having all three gives us a very stable, strong structure connecting the two spacecraft and really helps with the GNC and the dynamic side of the problem. So we'll be moving through a bunch of maneuvers as a tandem team between the Swift mission ops and the Link mission ops teams in order to perform those inspections at various ranges as we come in and use that to buy down the risk of whatever our chosen grapple location is. I think one of the big challenges is that Swift has been on orbit for 22 years almost this fall, and the multi-layer insulation on it is almost certainly not pristine anymore. So one of the big findings during various Hubble servicing missions was that the MLI covering Hubble was falling apart. It kind of turned into this very delicate, almost glass-like substance, some of the astronauts said, where if you touched it, it would just shatter and continue to break. That's very different than the flexible plastic blankets that were installed 20 years ago. So it's likely that there are torn off pieces of MLI on the spacecraft, that some things are no longer in the position that they were originally, or that the blankets have degraded to some degree that makes it more challenging to capture. That's why we have multiple options for locations to capture and a very versatile approach and a very flexible team.
And we'll keep you posted on future space shows on the progress of that mission to reboost the Swift satellite.
Local, live, and community-based. Southern FM.
Yes, we certainly are local. Now we're going to play a recording we made at the Space Association of Australia meeting about the Western Australian Optical Ground Station.
Okay. Well, yeah, thanks very much for the opportunity to talk to you tonight. It's been really great as a massive space fan myself. It's really great to see such a big audience. I'm here to talk about a new facility that we're building in Western Australia called the West Australian Optical Ground Station. But we're only a few days off realising this, and I'll tell you a bit about this as we go through. So just to give you a bit of an outline of the talk, I'll introduce optical communications and some of the benefits to traditional radio communications for space. But then I'll describe some of the challenges of having laser links, so these optical communications through the atmosphere, and what our work here at the University of Western Australia has done to address those, and how we're leading some of those developments around the world in that area. And then I'll go into deployment progress for this ground station, and then finish up with some next steps and future aspirations. And I guess I also just want to acknowledge the research support that we've received from these various project partners and funding agencies and space agencies. And of course, thanks also to my research team who have done a lot of the work that I'll be presenting tonight. So just a bit of an introduction then, I guess, to the group and the overall research area on space in the University of Western Australia. So my group is about 10 people at the moment. We have 5 research staff and several PhD, masters and undergraduate students all contributing to the work. Our group is part of UWA's International Space Centre, which was formed about 6 months ago. And you can see some of the key research activities that the University of Western Australia is doing. So we've got our laser communication timing, which is one of the activities that I lead. But we also go right across the space spectrum, from remote sensing, astronomy, in this case, astronomy from space, dedicated space situational awareness, and then there's a number of others. And there's always some very interesting stuff happening. But now talking more specifically about optical communications, why are we interested in developing optical links to space over radio links? And a large part of that reason is that if you can have the technology that sits on the spacecraft is low power, size, and weight. And that is really ideal for this next generation of these satellite constellations, like for instance, the Starlink satellites, or just more generally, the push to go into smaller and smaller satellites. So you don't have necessarily the big space and capacity to have a big radio communications dish on your spacecraft constellation. And the other big reason is that a laser beam, which is used for optical communications, is highly directional. So while a radio wave from a reasonably sized dish on a satellite in orbit might make a footprint of communication signals on the Earth that might be hundreds of kilometers across to continental scale, a laser can focus its communication area to perhaps tens or hundreds of meters. So that means that multiple users in space and multiple users on the ground can communicate and use those signals independently of each other without fear of interfering or disturbing anyone else. And that avoids one of the most costly components of space development, which is this spectrum crowding. So when a new satellite launches, there's this auction to give it a bandwidth over a particular geographical area in the radio domain. So with lasers, you can avoid that. So that's the general benefit. And some of the reasons we're particularly interested in this is that optical communications opens up these novel capabilities. So not only are they lower power and more directional, but we have the ability to make much higher data rates. So sending data from space to ground much more efficiently, so thousands of times more bandwidth than you can currently. And that's one of the things we're funded to explore with the SmartSat Cooperative Research Centre. Then another is quantum communication, and this is where you can have fully encrypted communications from space to ground and different from ground to space and then to somewhere else. And that's completely unhackable because it's secured by the sort of fundamental properties of physics itself. And again, we're looking at that with a research group and as well as the Australian Army. And then sort of more on the science side, we can do sub-femtosecond timing. And this is for measuring the flow of time between ground and space extremely precisely. And this has implications for science applications, such as investigating, things like, is Einstein's general relativity, wrong, or where does it break down, searching for dark matter and things like that. And we work with some French colleagues at the French Space Agency on that project. And then finally, sort of back more into sort of practical applications, we can do nanometer level positioning. So imagine like a next generation, GPS system, but instead of giving you locations to the meter, we can really narrow that down to, fractions of a meter. Not so important necessarily for a car driving on the road, but there are some reasons you might need to know your satellite positions very accurately. So look, that all sounds really great, but if optical communications, is so wonderful, then why aren't we really doing that already? And the big issue here is, Earth's atmosphere is in the way. The atmosphere is doing all the time, so it's swirling around. It's moving, and just like we look at stars at nighttime and you see them twinkling, a laser beam sent through the atmosphere is also going to get bent and deflected out of the way. So really you have this issue of atmospheric turbulence, and I'm sort of trying to highlight here with these words on the screen, they're ridiculously hard to read because all this turbulence is in the way. So what we really need is a system for eliminating the turbulence of the atmosphere, just making all this go away, and then we can really get to the benefit of laser communications that I talked about. And so just a couple of things I want to point out, that this atmospheric turbulence really does two things to the beam. So one is it kind of deflects the beam crosswise in the direction of motion. So it ends up making the beam point off target. So it changes its amplitude over time. I should say this sort of changes in the atmosphere happen hundreds of times per second. And that's the twinkling that you see as you go up and look at stars at night. But importantly, it also changes the time of flight in the direction and the line of sight of the laser beam, and that degrades the measured performance of the data, of the timing, and of the positioning. We call this phase noise, so it adds phase noise to the signal. And if we want to, really use optical communications to its full potential, we need to have different systems that suppress both of those effects. And at the University of Western Australia, we've built exactly such a system, and this is how it works. So on one side, we have a transmitter. We send that through the atmosphere into a receiver, and we, pass it off to the user at the far end. in order to suppress the atmospheric turbulence, we can have a little mirror at one end. So mirror the satellite, we reflect some of that light back and mix it, beat it against the signal from another mirror, and then detect that signal and electronically filter it and find, and by measuring those changes, hundreds of times per second, we can, just like noise cancelling headphones, we can sense what the link is doing and apply a correction to the timing of the laser that goes out, so that by the time it gets back to the receiver, back to the satellite, the time of flight variations are completely cancelled out. But at the same time, I said the beam also deflects, left and right and up and down. So in the same case, we have to build these optical terminals that can adjust, make fine adjustments to the pointing of the laser beam, again, hundreds of times per second. And the way we do that, we send the beam out and the beam also comes back, and we tap off a little bit of that light here, and we have a position-sensitive detector, so we can see if the beam's going up or down, left and right, and again, we filter that electronically and then feed that back to a mirror that can move hundreds of times per second to keep the beam pointing in the right spot. Of course, we do that twice, then the beam will always be pointing in the right spot. And again, we've built these little terminals, these little telescopes that shoot the beam of light exactly where we want them to. So one of the fun things we did is we packed up those systems in boxes, and we sent that over to our colleagues in the French Space Agency, and we deployed those systems between two buildings to see how well it would work. Critically, we also had a sort of fiber link between those two buildings, so we sent one signal over the air and stabilized that, and we sent another on the fiber, which we knew we can do a really good job at, and then we can compare the two and see how well we're doing. But we had a really great time, and the system worked really well. So that was great, and we could see that our system was working really well. But we wanted to really push that, and we then came back to Australia, and we put it on a much longer link from the University of Western Australia to another building and back. And importantly, this horizontal link has the same amount of turbulence as a link going all the way to space. So even though it's only relatively short, a few kilometers, because the atmosphere thins really quickly, as you know, if you're shooting a rocket, you get to max Q pretty quick. The same is true for the laser beam. So as soon as you get within a few hundred meters above the surface of the Earth, the turbulence reduces very significantly. So this is the perfect test bed for testing our technology. The take-home message is that we're able to improve that system by another factor of 10, even though now the link's turbulence is much greater. And so the key outcomes are that we can, we've made the best ever transfer of frequency, like these sort of timing signals for fundamental physics measurements, better than anyone's been able to do before. So we currently hold the world record in that with this number. We're able to do this position. It's really a Doppler measurement, a velocity measurement of the far site, so about 2 picometers per second. So that's about 7 orders of magnitude better than can currently be done in the microwave domain. Of course, this is just over a link. We want to actually demonstrate it to space, but in principle, the system works really well. And then at the same time, we then put a data signal across, and so we could show that we have these fiber-like data rates, so 200 gigabits per second per wavelength of light. So for comparison, at the moment, the first satellites that use optical communications are doing about a gigabit per second at most. And so with this system, if you encode multiple signals on that laser beam, we predict we'll be able to do something like 30 terabits per second. So again, orders of magnitude more than can currently be done. So that's all really great, and I've wowed you with some fancy numbers. And it's one thing just to do that, in an experiment in a lab over a horizontal link, but we want to take the next step and actually do demonstrations to space and prove these systems. And for that, we're developing this West Australian optical ground station. So the heart of the ground station is this observatory grade 0.7 meter telescope. We set up our control room, and we've developed custom software to make the telescope work exactly how we wanted. So that's our plan, let's say a short-term plan for the next 2 or 3 years. And then moving on, our sort of next steps and future aspirations are then to move towards space. And so in the medium term, we want to make the first ground-to-space demonstration of this satellite laser ranging system. So the Doppler measurements that give us this higher precision navigation than that's ever been possible before. So we can do that by just reflecting off existing retroreflectors in orbit. We'll continue our development of our high-speed optical communications technology, and we'll work with our industry partners, particularly Thales Alenia Space, to put that product on their roadmap and develop into a commercial communications terminal that can be sold on their spacecraft. And then, very excitingly, from my point of view, we've just been funded from the Australian Space Agency to investigate the feasibility of providing optical communication support for NASA's upcoming Artemis mission to land the first woman and the next man on the moon in 2024 or beyond. So we'll be looking to support them with this ground station. And more in the long term, we want to provide this key timing link technology for these really exciting fundamental physics questions where you have to have these state-of-the-art optical atomic clocks in space and then measure any defects in general relativity and so on. But that's more of a 10-year project. So that's our next steps and future aspirations. So thanks very much for your attention.
Recorded at the Space Association of Australia meeting some time ago. That was Sasha Shidewi from the International Centre for Radio Astronomy Research in Perth. And much of what he was speaking there for the near-term plans and some of the long-term plans have now come to fruition. This is The Space Show.
The sounds of the Bayside, 88.3 Southern FM.
Well, maybe sure can't turn back time, but we here on The Space Show can. In 1966, the NZBC broadcast a program supplied by UNESCO called The Sky is the Limit.
This is the national program. We present The Sky is the Limit, a series of 3 discussions arising from the first meeting ever to be held on the use of space satellites in mass communication. The meeting took place under the auspices of UNESCO in Paris last December. Here now is Rex Keating to introduce the first program, which deals with the beginnings of communication satellites and their potential use.
Well, here in the studio, from left to right, going around the table, is Dr. Leonard Jaffe of NASA, that is the National Aeronautics and Space Administration of the United States of America. He's the Director of Communication and Navigation Programs in that body. Then there's Professor N.I. Krikikoff, who's the Professor of Radio Techniques at the Institute of Telecommunications in Moscow. And finally, Mr. Arthur C. Clarke, winner of the Kalinga Prize for the popularization of science in 1961, and the so-called father of communication satellites. Now, how on earth did you come by this extraordinary title?
Well, I'm not responsible for it. I don't know quite where I acquired it, but there may be something in the description. I wrote the first paper on communication satellites in 1945 and was preaching their possibilities for about 10 years before anyone took any notice. And I think the biological analogy is apt as far as this is concerned. My part of the work was very brief. I had all the fun and other people did all the work, so perhaps I am the father subject.
20 years is a long time in this day and age. So could we now start with first things first? What are communication satellites? Dr. Jaffe.
The communication satellite is a rebroadcaster, if you will, or a retransmitter of information in space that can be seen over large areas of the Earth at the same time.
And how does it keep in touch with the ground?
Well, it keeps in touch with the ground by using radio waves. You transmit radio waves from the ground to the satellite, and you receive radio waves from the satellite back on the ground.
Now, am I right in saying that it follows an orbit around the Earth, which means that it drops below the horizon and therefore has a very limited period in which it can be used at any one given point? Is that how it is?
This is true of some satellites. It is not true of others. As a matter of fact, the one that was advanced by Mr. Clarke in his first paper, the so-called stationary satellite, or the synchronous satellite, is a satellite which rotates about the Earth in exactly 24 hours, the same period as that of the Earth. And therefore, to an observer on the Earth's surface, that satellite appears to remain stationary with respect to him. So it never sets, but remains in the sky at the same point.
There is one in existence now. Where is it hovering?
Well, there are, matter of fact, 3 in existence. The SYNCOM-2 is hovering over the Indian Ocean at this particular time. SYNCOM-3 is almost over the international date line in the Pacific, and the first commercial satellite, Early Bird, is over the Atlantic Ocean at this particular time.
Uh-huh. Now, Professor Krikikoff, you were talking about the Russian satellite used for communications quite recently. Molnia, I think you call it?
Yes, that's Lightning. Lightning 1, in Russian language, Molnia 1.
What sort of orbit does it follow?
So, that's a satellite with elliptical orbit, which is flying not very high, some hundred of kilometers in southern hemisphere, but very high, 40,000 kilometers in northern hemisphere, and not above the equator as synchron satellite, and not around the meridian above the poles, but on inclined orbit. Therefore, this satellite remains great part of his turn time above the territory of my country, above Europe and Asia and Far East, between Moscow and Far East of the USSR. We have a regular transmitting of television program and multi-channel communications. It is simply useful for communication services and broadcast in my country.
Did I hear you say in the conference that energy on board the satellite was powered by radioisotope?
But not this satellite. In my country were launched simultaneously 5 satellites, and one of these 5 is powered by atomic battery. Mm-hmm. And it is also an experimental system, and it is necessary to work in this field because in some hours satellite may be in a situation of eclipse when the sun batteries are not under sunlight. And these hours, this time, these intervals, it's necessary to have another source of energy, and atomic battery may be very good for with long life, such a source.
Mm-hmm. In general, Dr. Jaffe, then you use solar cells, do you?
This is the current source of power, yes. Dr. Krikikoff points out all of the forms, however, of providing energy for spacecraft are being considered. Nuclear energy, solar energy, conversion of different forms. But in general, the sun is sort of a free source of energy there, and if one can make use of it, he tries very hard to do so.
Mm-hmm. Now, the use of these satellites puts up some rather curious problems, does it not? What I had in mind at the moment were rather odd legal problems. They say that the law lags behind technology always. I think it's probably very true indeed where satellites are concerned. Now, Mr. Clarke, we might talk about this.
Yes, we have leapfrog our technology at such a rate that we're ahead not only of the law but of our thinking and our social customs. I think that, in a way, this is a bigger breakthrough in communications as the invention of the printing press, and we know what a change that made to society. It will really mean the abolition of distance, because every conceivable type of telecommunication service can be made instantly available to any spot on the Earth. I mean, apart from the obvious things like radio and TV, There'll be flow of information to computers. All the world's computers may be linked together in one vast network so they can talk to each other, and all the world's libraries may have instant access to each other so that anybody anywhere can ask for a document, which there may be only one copy of this document in existence, but they will have a facsimile displayed to them within seconds if they dial the right number. This is just a sort of beginning of things, perhaps ultimately even such things as specialized operations will be carried out through satellites. I can see the day coming when, if there's only one brain surgeon to do a particular kind of operation and he's in Moscow and the patient is in New Zealand, that'll be no problem. The operation will be done via satellites using the kind of technique for remote manipulation that now exists for work with radioactive isotopes. So a man will do work, his hands will be, say, 10,000 kilometers away from his brain, but he'll still be able to work just as though the patient is in front of him. Mm-hmm. Think of all the lives that sort of thing could save.
Coming down to earth a little more, it occurs to me that if you're using a satellite to cover a number of countries, a little problem such as that of copyright arise, which are practically insurmountable as things are today, and presumably this will mean a whole new range of thinking, a new range of international legal procedure. Another complication, surely, will be the frequency complication, the allocation of the various wavelengths to be used by the various satellites.
Yes.
May I ask you, Dr. Clarke, what do you think about the future of individual communication sets? It seems to me that after 10 or 20 years, every person will wish to have personal telephone set such as a transistor receiver now, and a little later maybe television set. Then we shall have a very large system of communication with very great needs in frequencies.
I think it's inevitable that we will have this kind of a personal receiver so that everybody has their own telephone, and you can call anyone in the world without knowing where they are, just by dialing a number. Now, this is in many ways a good thing, but in other ways it's a terrible thing, because it means you'll never be able to hide
no
from
privacy.
anybody. No privacy.
I was fascinated to meet a man whose company was actually selling satellites. Dr. Jaffe, can you tell me how much a satellite would cost if one wanted to buy one?
Well, you've asked a very difficult question. We don't really know what the operational costs of satellites are or may be, because we have not had enough time with satellites nor enough statistical experience to know how long these satellites are liable to last. Reliability is a tremendously important factor, or a lifetime of these satellites is a tremendously important factor in the cost of such satellites. So with that qualification, I can give you some rough numbers. I would say that the launching costs in our country vary from anywhere from $1 million for very small satellites that weigh perhaps 20, 30 pounds to $30 or $40 million for very large satellites. The kind of satellite that we have generally been talking about in the communication satellite business is launched with boosters that in our country cost between $3 and $10 million. So this is exclusive, again, of the cost of the satellite per se.
So for $10 million, you could buy a satellite and get it put into orbit, roughly, could you?
Of a rather small size.
May I point out that there are already in existence enough boosters to launch all the satellites for any conceivable communication system, and it'd be a great, wonderful thing for the human race if all these boosters, which are now sitting with nuclear bombs on top of them, were used instead to launch satellites. Then they would cost nothing.
Well, now, Mr. Clarke, quite recently I produced a series of radio programs called The World in 20 Years, in which a number of scientists contributed to what they thought the world would be like in 20 years' time. Some people it would be a very unpleasant world, others may like it, beside the point. Would you like to now become the grandfather, shall we say, of the communications satellite, and look forward to what your grandchild is likely to produce in 20 years' time?
Oh, my goodness. Well, in 20 years, we'll clearly have a world which psychologically is no bigger than a small city. And already we're taking transatlantic, transcontinental TV almost for granted. I mean, inside 1 or 2 years, this psychological change has occurred. And this is going to continue. The whole concept of distance is going to disappear. Of course, the development of supersonic transport is going to accelerate this. And we have a very interesting problem here, because we have two trends which are producing opposite effects. One is it's becoming very easy and quick and also cheap to get from one place to another. On the other hand, it's becoming less and less important to go from one place to the other, except for vacation purposes and amusement. Almost all the aspects of business and production can be done through telecommunications. So which is going to win out? Transportation and communication. They're opposing factors. In a world of perfect instantaneous transportation, you wouldn't need any communication. In a world of perfect communication, you wouldn't need any transportation. Which is going to win in the long run? I really don't know. But on that question really depends the shape of the future.
That was the first in a series of 3 programs on the use of satellites in mass communication. Under the general title, The Sky's the Limit, the programs are introduced by Rex Keating and were recorded in the studios of UNESCO in Paris. This is the national program. The time is 3:15.
And the time is 8 o'clock, 20 minutes to Purple Haze. Now, unfortunately, I did not record the other 2 programs in that UNESCO series. Richard, you're a man of the future, whereas I'm obviously a man of the past who could record something in 1966. Do you recognise any of the predictions made in that program?
Oh, they did pretty well on a lot of that, I reckon, particularly the communication front. It'd be nice if the travel was instantaneous now, but that's probably not on the cards. But the communication definitely got there.
Yeah, they thought that communications might outdo travel.
Yep.
But in fact, mass air travel has come along.
Yep. Although not so much the supersonic variety, but
yes. Okay. And of course, did you recognise the prediction of the internet?
Yep. I heard that.
And do you use the internet to look up things?
Occasionally, I might jump on the internet to Google something.
Because I've seen you pull out your phone and
yeah, it might have happened
and quickly look up something. Yep. And yeah, and of course now we've got lots and lots of satellites. We've got Starlink, OneWeb, Amazon, China putting up lots, and there's more than 10,000 satellites now being put up,
competing for space up there.
But they addressed the cost of the launch.
Yeah.
Now it's a lot cheaper, isn't it?
It's coming down. Reusability.
Coming down. And one company's been mainly responsible for that.
Yep, we know which one.
Although there is one operating from New Zealand
That's right.
that can put things up relatively cheaply. Well, before we go to our station announcements, we've got one more look back in time. And this concerns Soyuz 21. Now, during the 1970s, the Soviet Union launched a series of orbital space stations. Not all were successful, and not all were named. In 1976, June the 22nd, Salyut 5 was launched by a Proton rocket from Baikonur Cosmodrome in Kazakhstan. On 1976, July the 6th, the Soyuz 21 was launched with a crew of 2 cosmonauts. Next day, the pair docked with the Salyut 5 and boarded the military space station. 1 month into the mission, we heard this report.
Space station are feeling well, but facing a psychological problem after more than 40 days in Earth orbit. His bestie says the 2 men are in a state of sensory deprivation, having been cut off from normal sights, sounds, and smells for such a long period. On the advice of psychologists, Ground controllers are providing the cosmonauts with more news from Earth and are playing music for them during communications sessions. There's still no word on the expected length of the Institute mission, but Western experts say the cosmonauts may try to break the 84-day American space endurance record.
To this day, reports give conflicting accounts of what actually happened. Some say that the crew were affected by nitric acid fumes leaking from Salyut 5's propellant tanks. Others say the crew failed to follow their physical exercise program and suffered from lack of sleep. Others say cosmonaut Vitaly Zolobov suffered from space sickness and psychological problems. Well, we heard this report.
Are preparing to return to Earth. Reports say they're likely to make their descent within the next 48 hours. The BBC science correspondent says the announcement came as a surprise. It had been widely predicted that there would be an attempt to break the American-held endurance record of 12 weeks. However, our correspondent says medical reports may have made the Soviet authorities decide to bring the crew back. The government newspaper Izvestia said a few days ago that the cosmonauts were asking more frequently for news from Earth and that they seemed to be suffering from a feeling of growing isolation.
The Soviet news agency TASS says the two cosmonauts who've been orbiting the Earth aboard the Salyut 5 space station have now returned to Earth. The cosmonauts, who spent 49 days in space, are reported to be in satisfactory condition. Salyut 5 touched down in a preset area in Kazakhstan.
88.3 Southern FM.
On air and online via the free Community Radio Plus app. Download it now from the App Store or Google Play.
You're listening to The Space Show, and we're now going to present episode 3 of the Carmen Project. Now, the Carmen Project is an effort to set the groundwork for strategic discussions on the future of space cooperation for positive effect. William Gerstenmaier is Vice President of Mission Assurance at SpaceX. In this discussion, he describes how he worked to support the STS-1 as an engineer, STS-1, of course, being the first space shuttle flight. Here's William Gerstenmaier.
I would say my first launch of humans was the first shuttle flight 1, STS-1. Bob Crippen and John Young were the crew members. I was a pretty new engineer. I had done some work in Cleveland for 3 years before that, and then I went to the Johnson Space Center. And I was at the Johnson Space Center about a year before the first flight. I don't think as a young engineer I fully appreciated the gravity of what we were doing and how difficult we were doing. If you think about it, it was pretty amazing. Here's this space shuttle that had never flown in space before, and we're putting 2 people on this spacecraft that has never flown in space, and we're going to go fly them around the Earth. We had spent, probably 10 years preparing and training. I was in the back room learning how to operate systems and understanding the propulsion systems on board the shuttle. So we were pretty focused on our job, and I don't think I really totally appreciated the complexity of what we were doing. But then the launch went, the cruise on orbit. It was tremendously exciting to see all that happen. I mean, it's like any kind of celebration where, you spend your whole life kind of working for something. It seems like, like maybe college graduation, you've spent all this time getting ready and then the big event happens, or say maybe taking an exam, right? It's kind of like taking an exam. You prepare, and then pretty soon you're worn out. You can't prepare anymore. You go to sleep, you get up, you go take the exam, and then it's over. And then you kind of don't know right away whether you passed or failed in the exam world. In the space world, you kind of know right away. Either the launch went well or the launch didn't go well. So you get that immediate gratification that, hey, this went pretty good. And I think if you go back, I think probably that day I reflect back on all the activities that went, and I'm thankful for all the things that we did to get prepared. So I think I kind of reflect and and there's maybe a piece that we're there. I would tell you it's still not over, right? Because the crews are still on orbit. They still got to come back and land. So that's kind of the first step. So that first night you sleep kind of okay just because you're tired. But then like the second night, now you're a little more rested and you're thinking like, oh man, they got to come home. Are we really ready to bring them home? So then you probably don't sleep for a couple more days, right? Or a week or however long they're on orbit, or in the case of space station, it's 6 months. And then they finally come home. And then when you finally get to see them back on the ground, and that's when it's really special. When they've been to space and they're down on the ground and you get a chance to go talk to them, and then they just share what they experienced and what they saw. You get to ask them questions. It's just an amazing activity. So I can't think of a better endeavor of getting a chance to work with this group of astronauts that are just phenomenal human beings, as well as the engineers on the ground. Just a tremendous achievement. So there's not a simple answer of what it's like for that first night's sleep, but it's pretty rewarding business to be in. There's tremendous highs, and then as I described to you earlier, there's also tremendous lows. But it is a great business to be.
William Gerstenmaier, formerly of NASA and then of SpaceX. Katherine Bennell, at the time this was recorded, was Capability, Robotics and Automation Lead at the Australian Space Agency in Adelaide. And when she was presented with this quote, "We set out to explore the moon and instead we discovered the Earth," Katherine gave this response.
Yeah, we set out to explore the moon and instead discovered the Earth. I think when we set out to explore the moon, it was seen as something almost unattainable. My understanding is when that objective was set, we didn't even know if it was possible. And so to do an endeavour like that requires a huge amount of challenges to be overcome. It requires incredible amount of teamwork and a lot of things to go right, and a lot of cultural shift of thought. And when it's achieved ultimately after all the sacrifice in both effort and lives, and that achievement meaning something, it was a concrete step for humanity. It's something that is an achievement that will be remembered if memory goes so far into thousands of years, because it's something that is a tangible step forward in what it means to be human, to be able to go to another world in our solar system, that being the moon. And so when humanity takes a step forward like that, it's impossible to not reflect on what the world's like. And what the world was like back then was in a bit of a crisis, of course, in that era. And so a lot of the astronauts had this so-called overview effect, where they look back at the Earth and all of a sudden it looked fragile and all of the Earth's problems seemed minimized. And they conveyed that as best they could to the public. So as part of that, I think on Earth we discovered new perspectives about Earth, about ourselves, in creating that moonshot. And the technology that was developed in the course of that, of discovering the moon, was then also used to learn even more about the Earth. You know, we started having Earth observation for science, and Earth observation for helping eventually industry and all sorts of different applications, which helps us to learn more about the Earth more literally than figuratively.
The thoughts of Katherine Bennell from the Australian Space Agency. Jean-Jacques Dordain was the former Director General of the European Space Agency, and he responds to the question, how do you ensure a common ground in space?
I think that the future of humankind on planet Earth does not depend on 1 or 2 or 3. It depends on 7 billion of people. And this is the reason why I think that all these movement, which is called New Space, with the arrival of new actors and especially private actors, is very important. Because during several decades, space was mostly a top-down activity ruled and financed by governments, which was okay because we have developed all the technologies during that time. But now it's time to have another movement, which is much more a bottom-up movement with more and more people considering space as an important part of the future of humans on planet Earth. And that this is very good news, because this is by combining the top-down approach and the bottom-up approach that we have a chance. It will take time, but we have a chance to make all humans becoming actors of their future. And maybe not their future, but at least the future of the following generations.
In 2019, a global collaboration of more than 200 scientists obtained the first image of a supermassive black hole. Sarah, a member of the Event Horizon team, was one of them at the University of Amsterdam.
The heavy elements in our blood, everything that we need to be alive on Earth had to come from the explosions of stars and the formation of black holes, right? I've worked modeling this black hole since I was a student, so I feel, very attached to it. I dream about science, I dream about math sometimes. I try to imagine, what it would be like if I could somehow fly there, and how would it really look? We're part of the universe that created these things. We have the consciousness to understand them. We get to the point where we can start to explore distant objects and try to understand this weird multi-dimensional space that we live in. This space-time is almost like a fabric, and so this fabric you can think of as is falling into the hole at the same speed of light. So light itself is like a fish trying to swim upstream, it can't get out. It's a personal thing to be able to understand them as well, I think. And it's also the fact that we're related to them. We're connected. When I realized that I was one of the first group of humans ever to see a black hole, right? Because we were this limited team of like hundreds of people. It's it's not often in life that you feel unique.
And that was Sarah Markov, the woman who stares at black holes. All right, well, I'm Andrew Rennie, and we'll be back next Wednesday at 7 o'clock to bring you more news from what's happening in space.